I think this one was from quiz 11 or last one. I don't know. It is a little bit complicated problem. At least it looks so. But it's a nice problem. The problem says we have a plank, a rectangular, let's say, top of a table, whatever. It's rolling on top of these two cylinders, okay? And the cylinders are not slipping. They are rolling without sliding, without slipping. And this plank is pushed by a force. This force is given as 250 newtons. And the radius of the cylinders are given, 20 centimeters. And their masses are given, 10 kilograms. They are cylindrical in shape. That means the moment of inertia is 1/2 mr square. And what else is given? Everything is given in here. And the question is, what is the speed of the plank after it has moved 2 meters from rest, starting from rest? The force pushes it with a force of 250 newtons. And after it goes 2 meters, it moves 2 meters with respect to the ground. Okay. What is the speed? So the first thing that you have to be careful about the motion of the cylinders and the motion of the plank. Okay. The center of mass of the cylinders and the motion of the plank moves in somewhat differently. Okay, that's something you know from this rotational motion of wheel, or the translational motion of the wheel on a surface. Both it's rolling without slipping and it's going with some speed. So we have already know that I have shown you the top point of the wheel. Any wheel which is going on the surface moves at a speed 2 times larger than the speed of its center of mass. This is something you have to know. Okay? And I think you already have justified about this, right? Any questions about this? If any rolling object moves without slipping on the surface, its top point always has the twice speed with respect to the speed of the center of mass of the rolling object. And that means its linear acceleration is twice, its distance that this point moves will be twice than the distance taken by the center of mass. So that means if the plank moves 2 meters, then the cylinders will move 1 meter, right? So the rest is, once you fix this relation between the quantities of the speed of the plank and the speed of the cylinders, and their also accelerations, you can just write down the Newton's second law for plank and for the cylinders and solve it to find A, the acceleration. Because the thing is, if you are asked the speed, at the end of the day, you have to use this formula, and this you know from the chapter 3 or so, your earlier chapters. If you are given the acceleration and distance, then you can find velocity without thinking about the time. Right? This is v square formula. And we will apply this formula to find the velocity, but before that we have to find the acceleration of the plank. That's something I have shown as AP. P stands for plank. This is the top rectangular object. And the thing is, the speed of the plank must be twice the speed of the center of mass of the rollers. And the distance taken by the plank must be twice the distance taken by the center of mass of the cylinders. And the acceleration of the plank must be twice that of the center of mass of the cylinders. So once you fix this, you can draw the free body diagram for both the plank and the cylinders. If you think about the plank first, since we have an external applied force F, and also we have the frictional force between the plank and the top point of the cylinders. If you ascribe F1, one of the frictional force, as the frictional force between the plank and the cylinders, then the plank will experience twice this frictional force against the applied force F. That means your net force on the plank is F minus 2 times F1. F1 is the contact static frictional force between the cylinders and the plank. It's not a kinetic frictional force because the point that touches the plank is not sliding, right? So this is the first equation, and I think we have no any difficulty to realize this equation, just Newton's second law. But the acceleration is the acceleration of the plank. This acceleration is not the acceleration of the center of mass of the discs or cylinders. The second equation is about one of the equations of motion of the cylinders. Let's think one of them. If you look at the free body diagram, since the cylinders are moving and the plank is touching at the top, there must be a frictional force that moves toward right, because if you push the plank, then the cylinders will roll in the direction of the push. That means the direction of the frictional force must be to the right, in the direction of the plank. And this is something we know earlier from our spool problems. And this is always in the direction of the motion of the center of motion of the cylinder. So these F1 and F2. F2 is the frictional force between the ground and the cylinder, and F1 is the frictional force between the plank and the cylinders. Anyway, so these two forces are in the same direction. That means the net force is F1 plus F2, and this will be equal to m times A. Small m is the mass of one of the cylinders, and this A is the acceleration, center of mass acceleration of the cylinders. And we already know that this AP is twice of this A, and there is a relation between them. And this relation is here, okay? We are not done yet, because we have also the rolling motion, okay? And this rolling motion needs torque equation. Whenever you have a rolling without slipping, then you have to find a torque equation, and this is the rotational or rotational dynamics, rotational counterpart of the Newton's second law. The torque on one of these cylinders must be equal to the cylinder's moment of inertia times alpha. And alpha is the angular acceleration of the cylinders, and again, this alpha is related to the center of mass acceleration of the cylinder. This alpha is nothing but A divided by R. R is the radius of the cylinders. But when you look at the net torque on the cylinders, these two forces will not do the same thing, same job for the cylinder. One of the force will try to rotate the cylinder in the clockwise direction, and the other force, F2, will try to rotate the cylinder in the counterclockwise. So the net force, the net torque, must be the difference between these two, F1 minus F2, times the radius. Okay? And I think this also makes sense for you. And the fourth equation, I have not numbered as the fourth, because I is already, 1/2 mr squared, the moment of inertia of one of the cylinders. So we have these three equations, and in these three equations, some of the quantities are related to each other. And by solving these three equations, you will be able to find F1 as 3 divided by 4, the mass of one of the cylinders, m times a. And in terms of the Planck's acceleration, this is equal to 3 to the 3 by 4 divided by m times ap divided by 2. So from this, you can easily find the acceleration of the Planck in terms of the applied force. So this is 4f divided by 4 times mass of the Planck plus 3 times mass of the one of the cylinders. This is the end result. And if you put the numerical values given in the problem, you find the acceleration of the Planck as 100 divided by 35. Any questions so far? I know this is somewhat more complicated question. Yes. I have used in this equation. If you work on these three questions, okay, just an algebraic equation, then you will see by yourself. So the rest is easy. Just put this AP in this equation, the last equation, VP square, 2AP times delta x. Delta x is given 2 meters. And from this, the speed of the Planck after it moves 2 meters, 3.38 meters per second. Well, you will never have this complicated problem, this kind of complicated problem in your final. You don't worry about, but just for the sake of the knowledge of this chapter or the application of the concepts of this chapter, it is good for you to appreciate this problem. Okay. Anyway, if you have further questions, you can always ask me after the problem-solving session. This one, I think, again, is from the quiz 11, and I've just put this solution. I have done this last week. I don't remember that right now. Let me just read it. Maybe you should read it also. Okay, so in this problem, it says you have two round objects. One is a sphere, solid sphere, and the other is a hollow sphere. Its inside is empty. Well, if you check my notes, you can find their moment of inertia, the expression for the moment of inertia for both solid sphere and the hollow sphere. They are different. For solid sphere, it's 2 divided by 5, the mass of the sphere, times its radius square, but in terms of the diameter, of course, d square over 4 is the expression in terms of diameter, because diameter is half of the radius. And for the other object, hollow sphere, the moment of inertia is somewhat different, not 2 divided by 5, but 2 divided by 3, m times radius square or diameter square divided by 4. This is the expression for the moment of inertia. It says the kinetic energy for the hollow sphere is twice of that of the kinetic energy of the solid sphere. By comparing these two expressions, two kinetic energies, 1/2 I1 omega square and 1/2 I2 omega square, for both, it says their angular velocity is the same. So you put the same omega for both rotational kinetic energy and just compare these quantities. You will see, since they have both the same diameter, when you compare it, you will find M2 is 6 divided by 5 M1. For those of you who have seen these questions in quiz 11. Not everybody have seen this question, but some of you have encountered this question. question anyway, I will put this solution and the problem in the lecture notes today, right after the class, so you can check. And there was this problem. It's very small. It's hard to, but probably you have realized this shape from the quiz. How many of you have faced this question? There is an X, and there is a ring. It's rotating around this X. Some of you have encountered this. Only the point D, I think, I have to check. Okay, this disk you see on top left rotates around this X, and the moment of inertia of the disk is given, and its rotation in terms of revolution per minute is given. Okay, and this disk rotates 24 revolution per minute. So to find the kinetic energy in terms of joules, you have to convert first this omega into radian per second. Otherwise, your result will not be in terms of joules. So 24 revolution per minute can be converted by using this conversion chart. One revolution makes 2 pi radian, because these ratios are equal to 1. I can always write down these ratios as multiplication to 24. One revolution is 60 seconds, and 2 pi radian is 1 revolution. When you do this, revolutions will go, and radian per second will stay. So 24 revolution makes 24 times 2 pi divided by 60 radian per second. And you will take the square of this to find the kinetic energy. So the same problem, but the question is different. Again, this time I think you can read. This is the top view, and this is the side view of this. This disk is rotating around this X, this perpendicular vertical X. And the question is, the moment of inertia is given of the shaft. It says this point Q on the disk. What is the acceleration of the point Q on the disk if it rotates uniformly with a speed of 43 revolution per minute? Again, there is a conversion. You have to be careful about these conversions. And the acceleration is asked in terms of meter per second square, so you have to convert revolution per minute into radian per second. Again, the same conversion. 43 is 43 times 2 pi divided by 60 radian per second. And the acceleration, the radial acceleration in terms of the angular speed is given by omega square times r. And you know, we always used this another formula for the acceleration in the uniform circular motion in chapter 6. This was v square divided by r. But since there is a relation between v and omega, and v is equal to omega times r, it is preferable to use this form for the acceleration, because you are given omega and r, not the linear speed.
It should be overall, isn't it?
No. If you put, instead of v square, omega square times r square and divided by r, you have omega square times r. This is A. Okay. Well, another question about the same thing again. I will pass this anyway. I have solved this one last time, yes. And this one also is solved, right? This one we have solved. Okay. This is the question from your last quiz. And some of you have probably seen this question. There is a disk, okay, or a round object, whatever. It's rolling down an incline, a distance of 2.4 meters, and the incline has an angle of 30 degrees. The question is, if this round object moves 2.4 meters in 1.2 seconds, what is its moment of inertia numerically? So it comes from A to B. It starts from rest. Initial velocity is 0. It rolls without slipping again. Okay, there is no sliding. And what is the moment of inertia? How can you attack this problem? Well, if you think about the motion of the center of mass of this disk, what kind of motion it does have? Goes the center of mass, point mass. You think the point mass when it goes from point A to point B. What kind of motion is that? Is it constant velocity motion, or does it have a changing acceleration? Acceleration is changing? If the acceleration is changing, the forces on the object must be changing also, right? If you think the forces on the object, there is a gravity, and gravity is not changing because the weight of the object is not changing. Also, there is the frictional force between the rolling object disk and the surface. This force is also this constant, right? If the forces are constant, then the acceleration is constant. So the type of motion of the center of mass is a constant accelerated motion. It goes a distance of, let's say, this distance as x, whatever, okay. And in terms of time and acceleration, we know that for a constant accelerated motion, x is equal to 1/2 the acceleration times t squared, right? And if you look at the problem, given values in the problem, time is given, x is given. So from this information, I can find this acceleration of the center of mass of the rolling object, right? And I can calculate easily the acceleration as twice the distance it takes divided by t squared. And let's do this. 4.2 times 2.4 is 4.8 divided by 1.2 squared. Right? What is it? 1/3. Are you sure?